So very good afternoon to all. First of all, I would like to thank the organizer and giving me an opportunity to talk about our recent work and the data-driven exploration of the swarmlators with the higher order harmonics. This is our recent work is done with my PhD scholar and Dr. Vikesh Chandrasekhar. So what is the aim of the work is to explore the occurrence of the various collective dynamical states in swarmlators with higher order harmonics. Okay. So the swarmlators, the systems in which both synchronization and swarming. So normally if you are going to consider the synchronization means the tendency of the periodic systems to align in time, or sometimes the people may consider the coordination of the entities to achieve order in the time domain. Usually the many peoples are working to understand, to study the collective behavior of the many coupled oscillators. So we can consider the many examples. And swarming means the aggregation or grouping of the coupled objects and the coordination of the entities to achieve order in this space domains. So one can consider the robotic swarms, insects, and others. So one can consider the many examples in order to understand the synchronization, the metronomes and swarming with respect to phase and location. So how we can model in synchronization and swarming? So the synchronization one can model with the help of the chromatophase oscillators in order to understand the self-organization in time. The behavior of swarm, one can consider the particle model to understand the self-organization in space. So swarmlators, the phase dynamics theta of I and spatial dynamics x of I, the both are coupled together. So here the synchronization theta of I, they influence each other. The one can consider the spaces are synchronized to a common value, otherwise it is synchronized to the different values. The location x of I is entities influence each other. It is physically it will attract each other and repel each other and based on the distance. Okay. But swarmlators we can consider both bidirectional coupling between the synchronization and swarming. Here we want to consider both phase and space. The theta I influence the movements x of I and the position x of I influence the phase dynamics theta of I. One can get many examples, the magnetic domain walls and genus particles. So this is the model we can consider the swarmlators, and this work was published in 2017, the oscillators that sync and swarm. Here the J and K which denotes the interaction strength between the oscillators in terms of phase and space. The epsilon and epsilon 2 which denotes some exponents in order to understand the interaction terms. The V of I which denotes the velocity and omega I is the frequency of that oscillators. So normally one can consider the values of J and K, the swarmlators which shows the different kinds of the collective dynamical state, the static synchronization and the static asynchronization and static phase wave state. So the static synchrony means it is a fully synchronized in phase. The static asynchrony which denotes the every phase occurs and everywhere. So okay. But once if you are going to consider the interaction strength and J and K, we can consider the active phase wave state and the static asynchronous state. So our preliminary study is, we have the swarmlators. We need to introduce some higher order interactions, that is the harmonics in phase interaction. Why these studies are very important? Normally the higher order interaction will shape the collective dynamics, but how they affect the transition between the different states in swarmlator systems. So we introduced some higher order harmonic terms in chromatome models. So we first consider the second order harmonics in the swarmlators model and their complete collective dynamical starts explored. The second, we applied a machine learning approach to investigate the system based on data-driven analysis to determine the classification of the collective dynamical states arising from the dynamics of swarmlators. So we also adopted some suitable machine learning approach of convolutional neural network and specifically employing the U-net neural network model. So we obtained the clustering and the active asynchronous states. The active asynchronous state means the each swarmlator undergoes the continuous positional changes within the radial disk. So this is our results. It is a clustered phi state. We are going to consider the swarmlators, the two groups which maintain some constant phase difference. And this is mixed phi state. So even though the two group of oscillators which maintains constant phase difference, but is randomly moving in the radial space. Okay, so other collective dynamical states also available. Right. So the problem is, we have the clustering mechanism. One can able to identify the clustering mechanism. So with the help of the Jacobians, and which obeys that the lambda, it takes the negative value, it is the stability through the stability analysis. So we can also quantify the occurrence of the different collective dynamical states. So even the clustering mechanism or a mixed pi state and others by using the suitable order parameters. The problem is we can't able to get the complete collective dynamical state with the help of the order parameter. The problem is the active asynchronous states which show some random nature in terms of the order parameters. So therefore, we adapted some machine learning techniques. So the purpose of the machine learning study is to understand the entire collective dynamical states. For this purpose, we utilized the 4 statistical metrics: the spread of the power spectral density and the instantaneous deviation from the time average and kurtosis and the skewness. So we consider some of the channels. With respect to the channels, we consider the mean speed, the time series of the swarmlators. So this is the mean speed, the time series of the swarmlators for active states and static state. From this, we pre-process the training data of the extracted statistical quantities after some reshaping techniques. And finally, we achieved the different collective dynamical state through the machine learning approach. Okay, so we investigated the impact of the higher order harmonics, particularly the H. The H means we considered some higher order harmonics through the phase interaction function, which shows the clustering states and clustered pi state and a mixed phi state. The higher order harmonics, significantly changes the dynamics within the interaction parameter plane, affecting the parameter regions of the various dynamical states. The emergence of the active asynchronous state, relevant to the biological phenomena such as the insect swarming and factorial mobility, which occupies the transitional region between the static asynchronous state and the active phase wave state. So we employed the convolutional neural network to identify the entire collective dynamical states arising from the higher order harmonics of the swarmlators. So thank you for your